Hello, everybody. I am Michael Botelio. I'm a postdoc at Yale working with Juan Laura. Probably not many of you recognize my name. I do a lot of work on Mars, not literally, but with Mars data and Mars data sets, and more recently with Titan, although I have done stuff with Earth before. This is a project that I've been dabbling with for many years now in my quote unquote free time, as I try to get a tenure track somewhere. So I'm really excited to be sharing this kind of work with the community for the first time. The last two presentations have really done all the introduction that I suppose I need to do. So I'll be able to get through this part very quickly. But we know that the anthropogenic warming that we're experiencing is changing the baroclinicity. And there are these kind of competing factors that have been looked at previously for why or how the baroclinicity and therefore storm tracks are going to be changing. And there are these competing effects as we change the temperature gradients. There's the horizontal temperature gradient, which is supposed to be weakening and will be weakening. And then the vertical temperature gradients will be changing as well. And there are these competing effects. And so some papers have speculated that maybe we're approaching the point of the strongest eddy kinetic energy. And whether or not that's the case, or where locally, maybe some places will continue to increase and others will decrease, or maybe we'll reach a slower change in time, has been an open question for a while now. There have obviously been a lot of studies that have looked at this question already. And a lot of the responses are, of course, highly dependent on season. You would expect that when the storm tracks are active in the winter, you would experience bigger changes than versus the summer, and that's truly the case. Additionally, you can look at different trends across different reanalysis data sets and make sure that they hold up. Here's an Edmund Chang paper from 2016 looking at that over a bunch of different reanalysis data sets. And the Pacific and the Atlantic are both seem to be increasing, at least from the metric of eddy meridional winds. Not only that, you can look at the Lorentz energy cycle and see how that's changing as well. And in the barotropic, the baroclinic term in ERA interim and INSEP R2, the baroclinic energy conversion is increasing along with changes in eddy kinetic energy as well. And the response barotropically is kind of maybe it's close to zero. It's hard to say. Additionally, a lot of people looked at the local energetics, particularly as we've just seen over the Pacific, because it has a lot of interesting features intrinsically to it as well. And there's been a lot of research showing that these changes in warming will affect the storm track in different ways, and the upstream side and the downstream side. And all of this to say is that as we continue to warm and continue to generate better and newer data sets, it behooves us really to continue doing these sorts of analyses to see what the response is in the storm tracks and why the storm tracks are responding, which kind of leads me to, as we get these better data sets and we get a better handle on how the temperature changes, can we better say what is the impact going to be? And are we really approaching the point where the eddy kinetic energy is maximized? And so thankfully, we've seen this equation twice already now, basically. This is the eddy kinetic energy equation. This is kind of the... Thank you, Siri. The eddy kinetic energy equation from Orlansky is shown here. And the terms that I've labeled, we've looked at the baroclinic energy conversion a lot. This is barotropic. These two terms together cannot produce or destroy energy. The E-trans, which is the EKE advection, and then the geopotential flux convergence, cannot create or destroy energy. It's really the two energy conversion terms, baroclinic and barotropic. And there's been some work looking at this cross-frequency eddy interaction term as well, and we'll look at that too. And of course, what you're left over with is the residual, and there's curvature terms, stress, numerical errors, dissipation errors, assimilation. We'll save that for another time though. So the data set I'm going to be looking at is ERA5. For the sake of not overwhelming our poor servers, I've downsampled to only 4 times daily and half a degree instead of quarter degree. And you've probably seen this figure several times now over the last couple of days, but I'm taking just the first chunk of ERA5 for now. Maybe I'll go back and look at the previous decades, but from 1980 forwards. And so what do these trends look like? What do these data look like? So here are the trends calculated every single time step, and I've globally integrated it. So I like this, the prefix here, which is YJ. These are yattajoules, which I find very entertaining, or exawatts, just integrated over the entire globe. And this messiness is just the raw, not filtered data, but these are eddies calculated between 1 and 10 sols. And then the orange line, I've low pass filtered it to take out the interannual variability, and then plotted the trends according to these lines. And so the trends look kind of small because I've had to zoom so far out because there's so much variability for most of the terms, but the terms are extremely robust simply because there's so many points in the data set. And here's what they look like: the globe, the Atlantic, the Pacific, and the Southern Hemisphere. The eddy kinetic energy seems to be increasing in all three regions and globally, as is the baroclinic energy conversion. The barotropic energy conversion varies more complexly, as I'll show you in a second, and the cross-frequency eddy interactions and the two transport terms, the EKE flux convergence, which I'm going to add together as being the advection and the geostrophic geopotential together, is kind of basically a wash in the global sense, as one might expect, basically. So we've seen how these changes respond globally and in different basins, but what do they look like locally? So on the left-hand panel here, I'm just showing the raw average, the whole 42-year ERA5 data set on the left-hand sides, and then the trends by linear regression are in the right-hand panels. So this is not going to be the average, is not surprising to anyone, I don't think, but some of the trends in this data set I think are particularly interesting. Australia has a decrease, Northern Eurasia is a decrease, the Eastern Pacific is also a decrease, and then everywhere else is an increase in the eddy kinetic energy. And while this term kind of looks small compared to the actual mean, when you multiply this by 42 to get how much it's actually changed over the entire data set, you start getting at many percentage points of change, 1 or 2 or 3% in different areas. And so this is an important effect. So why are these changes occurring in different regions? Well, let's look at the energy conversion terms. The baroclinic energy conversion, again, probably not that surprising in the overall average. The Southern Ocean stands out, as do the Atlantic and Pacific storm tracks. But within those two regions, we kind of see the general response of baroclinic energy conversion increases on the upstream side of the two Northern Hemisphere storm tracks. And there's this broad decrease in the baroclinic energy conversion on the downstream side. And we've had a couple of talks now looking at the response of the baroclinic energy conversion based off of how efficient it is being. And that's definitely follows through, and you can see that in kind of the overall global trends here. The Southern Ocean is more of an overall increase across all longitudes. Compare this now to the barotropic energy conversion term, which is a bit more complex to look at. It's kind of in the general sort of sense, you might initially say, well, there are decreases on the downstream side, except in the Pacific, where there's a decrease on the upstream side, and that in the barotropic sense, there is an increase. Let me go back a slide and show, here's that the decrease in the eddy kinetic energy is a decrease in baroclinic energy conversion, but is accompanied by an increase in barotropic energy conversion here. Additionally, in the Southern Hemisphere, there's this kind of splitting behavior here. And it's not something I looked at, but I'm really interested to see is whether or not the shifts in the jet are really focusing these kind of zonal mean structures in the eddy energetics together, because around 50 degrees south, there's this kind of overall positive, and then on either flank, there's this decrease in the barotropic energy conversion. This is even more complex if you look at the cross-frequency eddy interactions, where there's this kind of reversal from hemispheres. So I point out the zonal structure. it was positive for the barotropic energy conversion around 50, but it's reversed in the cross-frequency eddy interaction. So where the eddies are losing energy to the zonal mean, they're gaining it from longer period eddies. So there's this weird kind of this periodicity cycle going on here. And that's opposite in the northern hemisphere, though. So the center of the storm track seems to be gaining energy from long period or other period eddies in the northern hemisphere. So there's a lot of interesting stuff at first blush to look at. As you might expect, the energy flux convergence is really just responding to the fact that because there's more eddy kinetic energy to transport around, the terms are just being reinforced where they are in place. They're not really changing all that much. And just to compare the regressions that I've shown to kind of a 2-point regression, which is just compositing the last and first 5 years and then subtracting them, the regression is really pulling out where the biggest responses are. This is the eddy kinetic energy, and this is the baroclinic energy conversion. And with my last minute, I would be remiss as an early career person if I didn't shamelessly plug all of the other stuff that I'm doing. So you're just going to have to deal with that for the next minute. So some of my Mars stuff might be interesting for people listening, which is I've looked at the eddy energetics on Mars. There are actually 3 reanalysis data sets for Mars, believe it or not. NASA has had satellites in orbit for almost 20 Earth years now. And so we have pretty nice reanalysis data sets, and we can compare dust storm activity, which is, that's what this is. This is the Mars Dust Activity Database, which is a 15,000 member database that I created when I was at the Center for Astrophysics at Harvard, and can compare that to synoptic scale structures, and they match up really, really well. In fact, this sort of looks like a Norwegian cyclone model sort of thing, except we're looking at, dry dust and not moisture. So this is what the energetics from Mars look like. There's a really strong solstitial pause or a midwinter minimum on Mars as well. And that's something I'm actively looking at right now. This paper in JAZ is out as of yesterday. So please go find it, looking at and comparing the energetics in these reanalysis data sets. Finally, I'll just mention that I've also done some research looking at annular modes on Mars and Titan and how they respond to dust storm activity. And there's this leading behavior where you can kind of predict dust storms on Mars if you know the annular modes. There's a paper that I have out in GRL looking at the interactions between extratropical and tropical eddies on Titan. Go look for that. And finally, annular modes are similar across Earth, Mars, and Titan. Go see this paper in Nature Astronomy that I have out last year as well. And so with that, I will leave my kind of summary and conclusion slide up, and I'll be happy to take questions from all of you. Thank you for having me talk.
Thank you. So if there are any questions for Michael, please put them in the chat. I guess I had one. You started out with the motivation of trying to understand kind of the response to warming. And I'm wondering, do you think what we're seeing in the real world so far, like what's the relative roles of internal variability versus the actual response?
That's a good question. If you, something that I will be working on as I continue exploring this is, the overall trends that I've shown are now from 1980 to the present. And so you don't have to calculate over that whole period. You can start looking at trends within that to look at interannual variability. And that's definitely something I want to do. But if you just take, one, panel at this large zoomed out, you can see, even if you filter at 1 year, there's still variability inside the 1 year. But if you look at the kind of the individual little squiggles from individual years in this kind of qualitative sense compared to, I wish I had tick marks on the far end as well, but it's the individual squiggles are kind of order of magnitude, the whole overall trend. But because the regression is along all of these data points in time, the regression, the error bars for the globe at least are so tiny that the actual trend is robust, even though there are definitely changes kind of in the global sense. That'll be also an interesting question to look at locally as well, and I haven't looked at that yet. So TBD. Well, that's a great question.
Yeah, I suppose the more you average, the more likely you are to pick out the signal, except the southern hemisphere has the ozone depletion, which would complicate things a little bit.
It's another reason to stay away from 1950 to 1980 as well for now. So
okay. All right, there's another question in the chat from Sebastian. Do you normalize the conversion term because they are a function of the eddy amplitude, and it might be useful to normalize them before looking at the trend?
Yeah, in kind of I did play around with kind of subtracting means and doing normalizing, and it might be easier to visualize, but for the sake of I kind of wanted to show the actual amplitude in these figures versus the trend. Yeah, for presentation's sake, that might be an excellent thing to do.
Okay, yeah, maybe you can continue this discussion in the chat. There's one other comment and question from Mindy. Fascinating and impressive work on Mars and comparing to Earth with warming. I would like to hear more of your insight on the midwinter lull in Northeast Pacific in early February. Do you have any comments on that?
I am Linka Novak and I are kind of actively exploring this. Linka is kind of well known for looking at this, and we're going to, Sebastian did an excellent job, I think, with his 2018 and 2019 papers looking at this. But there's definitely something to be done in looking at, the barotropic governor sort of question as well, which a lot of people have kind of looked at and dismissed. But there seems to be, just going back, there's a lot going on between the barotropic and the baroclinic responses in the Pacific. And the next thing I want to do is look at seasonal averages and just to see what the baroclinic and barotropic responses are doing. But Lincoln and I have an idea or set of ideas to look at these responses in particular. And again, that's another great question, and it's another TBD question. I wish I had more concrete answers for all of you.